Thanks. Sorry, yeah, let's cut that bit out. Awesome, folks. Today I'm going to be talking about hyperorganic systems. I'll motivate as to what hyperorganic systems are, and then we can delve more into how we can design systems hyperorganically so that they adapt over time as well as evolve with the internal as well as external conditions of the systems that they're operating in. I am Shruti Appiah. I am chief economist at Huddle 01. My co-founders are right there. You can say hello to them. And I'm super excited to talk about hyperorganic systems. I want to motivate a little bit as to why we might hyperorganic systems, and particularly it's due to this fallacy of simplicity. We always tend to think that simple and static models are extremely predictable. But this can't be further from the truth. One of the biggest examples of this, I'm sure you're all familiar with, is Bitcoin. Bitcoin had an extremely simple economic model. It had a fixed total supply and no inflation, but it was designed to be a digital payment system. It literally says in the title of the white paper that it was designed as electronic cash. So it was supposed to be a medium of exchange indeed. And if we look at the history of it, ever since the token was launched, Bitcoin was launched, we saw that it went from sort of being a niche collectible back in the very, very early days. Then there was a brief period, perhaps I think in 2009 and 2010, where people were buying pizzas with Bitcoin, like 10,000 pizzas for 10,000 Bitcoin for 2 pizzas. And it none of the agents that were interacting with the system, none of the participants that were actually buying their pizzas with Bitcoin ever could have imagined what the future of Bitcoin actually held. So you can see that the use case of Bitcoin completely broke down from being an electronics cash medium of exchange type of system all the way to today. What it is indeed a store of value. It's a speculative asset. And this is the problem with static models. This is a problem with simplistic static models. Simple models are not necessarily bad, but if the simple models are rigid, then they can actually give rise to really unpredictable outcomes, especially when it has to do with these protocols, rigid protocols that are operating in a really complex and ever-evolving environment. That's why we need hyperorganic protocols. Hyperorganic protocols predictably preserve the function of your system. They predict the utility of the network and the function of your system in the long term, and as the environmental conditions change of your system, as well as how the agents interact and behave with your system. Awesome. So what are hyperorganic systems? Hyperorganic systems, by the way, I coined this term. So if you look into it online, all you'll find is my work. So better to just hear about it now for these 20 minutes. Hyperorganic systems are dynamically adaptive. They adapt to the changing conditions of the environment so that they can stay perpetually relevant. And they're able to change based on the current state as well. So they're always relevant to the current state. And as a result of that, they're also capable of being self-governing because the protocol itself adapts and evolves over time rather than requiring manual intervention to be able to change the protocol, change the parameters, or change even the policies that the system is operating in. So without requiring any manual intervention, you're able to actually evolve your protocol. And as a result of that, since it's not actually bound by humans and all of our flaws, such as the time that it takes for us to respond to changing conditions, it is pretty much unconstrained in terms of how much and how fast it can grow and evolve over time. I want to talk a little bit about why we might want hyperorganic systems and just summarize quite a few different points that it helps us with. It helps keep the system perpetually relevant because every single parameter as well as the policy of the system will stay perpetually relevant because it is being updated in the current state. Then the second thing is that since we don't actually require manual intervention, we can actually delegate chaos, and we can do so selectively. If we don't want to actually, you know, delegate certain problems, perhaps more complicated problems, to artificially intelligent protocols, then we may as well keep those decisions to ourselves while we delegate more simpler decisions to any kind of information processors that are involved in a hyperorganic protocol. And the third thing is that it helps us prevent systemic collapse that typically occurs when we have rigid systems that are incapable of predicting things in the future. And usually they end up being incapable because oftentimes rigid systems, they start with key assumptions that are set at the start of the system, at the initialization of the system, and they're not allowed to change during the lifetime of the system. And the fourth thing is that we're able to build these systems in a self-sustainable fashion. It doesn't require manual intervention, so these systems constantly adapt and evolve as time goes on, even without requiring any external intervention. So there are perhaps hyperorganic systems that can even outlive humanity. And the fifth one is that it enables us to escape local optima. Anytime we actually intervene into a system, we are usually doing that in order to escape local optima. So for example, if you think about central banks in the US, they are constantly recommending different interest rates so that they're able to rebalance the system. So that way, instead of requiring some experts that are actually rebalancing the system every 4 years, you're able to automatically and in an automated fashion escape local optima. And finally, we're able to prevent regulatory capture by incumbents. Hyperorganic systems are really, really apt to be actually built on these decentralized protocols because they are operating on collective intelligence rather than centralized intelligence. Central bank is centralized intelligence. It has a tremendous amount of experts from various different fields. However, at the end of the day, they are actually centralized intelligence. Similarly, we'll actually go through a really fun part where we look at the spectrum of mechanisms, where you can see between rigid mechanisms versus hyperorganic mechanisms, how rigid mechanisms are typically instituted by centralized institutions so that they can capture power. And typically, in the modern times, the biggest way that power is captured is through regulatory capture. And tangibly, this helps us in cryptoeconomic systems avoid freak liquidations because the economic system is able to morph with demand and supply. So if your system is experiencing some sort of downfall, then your economic system is also able to respond to that signal in an appropriate way so that it doesn't lead to a massive dump. Then the second thing is that it's able to grow the supply with increasing demand. So this really comes into play when we're actually talking about DePIN protocols. DePIN stands for Decentralized Physical Infrastructure Networks, and typically in DePIN protocols we use tokens as network utility. So they represent network value and network utility. We don't want to have a speculative asset in a DePIN protocol. So always when we want to preserve network utility as a function of the token, then it's really, really useful to have the tokens actually grow in supply with more value actually being input into the system. Then you can also have hands-off live execution. Of course, it doesn't require manual intervention, so it's hands-off. And of course, you can also manage future risk in a fairly smart fashion with the more sophisticated information processors that we have available to ourselves today. And finally, you're able to preserve the system's function because you're able to stay perpetually relevant. Here's a quick example of what might the evolution of a hyperorganic protocol look like. So you start from the left. We have a system that's just defined. It has static parameters. Usually these static parameters are set during the initialization of the system. These static parameters are very much so based on assumptions and based on our own predictions about the future. And for that reason, oftentimes it's not very accurate, and oftentimes it leads to the downfall and systemic collapse. Then in the second one, you can see that we've got hyperorganic policies. Now, instead of Y being based on basic numbers. Instead of it being a fixed parameter, we have y being based on functions of the current state. So function of x, x1, x1, x2, and x3, which all lead to are basically parameters of the current state. So those are hyperorganic policies. But if you want to build an entire hyperorganic protocol, you want to also enable the parameters to change, the policies to change, but the protocol also to be able to self-update itself based on new information coming in. And there's various ways that you can do this. One of the ways that is feasible is using multi-agent AI processors. It's basically information processors. And what's crucial is that since AI is not very powerful today, you need to also have human buffers, because that's what helps us essentially control the degree of influence that AI would have on the hyperorganic protocol itself. That's a hyperorganic protocol. I want to actually tie this to one of the talks that Angela was mentioning. This is the mystery of artificial intelligence economies. It's a talk that I'm referencing back to that I gave in Token Engineering 2019 back in Berlin. And the QR code is, yeah, you can scan it if you want to watch that talk. But essentially in this topic, we cover artificially intelligent economies where each agent acts as a reinforcement learning agent. Essentially, it's an AI bot that is operating in the economy in order to make rational decisions and maximize the return for the controller of those bots. And in the right, you can see game warping. Game warping is one of the dangerous scenarios that can occur when you have external transactions that are happening outside of the smart contracts. Since smart contracts are transparent and strictly enforceable, these kinds of scenarios are quite likely in smart contract systems compared to legal contract systems. And game warping, you can think of it as basically out of contract arbitrage. You can also think of it as essentially things that we see even in MEV are quite similar to what happens with game warping. And then we motivate as to why we might actually need to use reinforcement learning agents in order to actually analyze and prevent game warping as well. All right, so this is the fun part where we talk about the spectrum of mechanisms. In the very bottom, you've got simplistic changes that you can make to the system. So that's parameters. You can change the system at the parameter level, or essentially you can make your parameters more sophisticated, or you can change it at the policy level. Policies are essentially monetary policies or economic policies, which are functional elements of your system. So you can think of it as basically rules that the economic system is operating under. And finally, you have the protocol. Protocol is the encompassment of all policies as well as parameters coming together in order to form a coordination system, a multi-agent coordination system. And from left to right, you have rigid to hyperorganic. In the very left, you've got various kinds of things that we are working with in today's world that are fairly rigid. And they're simple designs as well. So, for example, the Fourier precedency term, like with what the number 4 is fairly arbitrary, right? So it's a rigid system, and it is also not very complicated. It's basically just a parameter that we have set. Then we go a little bit up, we can see the fixed supply of Bitcoin, which is also a parameter that is rigid. Then we've got milestones-based vesting as well as emissions and token vesting schedules. Those are also very rigid systems because they're based on time and because they're based on assumptions that you set at the start of the system. And then finally, you've got things such as Bitcoin as a protocol as well, which is fairly simplistic but also fairly rigid. But it's not as rigid as some of the other things that we've seen because it is still not possible to centrally control it. And perhaps in the highest level, I've got protocols and the laws of motion, perhaps one of the most rigid things. And I put this example in here because I don't want you guys to think that rigid is necessarily bad. We do need to have a sort of a constitution to operate in. And so the laws of motion is essentially the constitution for all of the physical worlds that we have opted into today. And so that is a rigid system. But you've also got human-created rigid systems, such as religion. That's fairly rigid as well, and it has been going on through centuries. Recently, as an update to ways that we organize ourselves as human beings, we've also got law. It's rigid, but less rigid than religion. We also have update mechanisms for law, so that's very good. And then perhaps the most hyperorganic protocol for multi-agent coordination that I could think of is language. And language is constantly evolving based on our inputs into the system, based on the socio-political conditions, based on economic conditions as well. And it is always responsive. It always stays perpetually relevant to the current state. This is the kind of protocol at one level that we actually need to be building with our economic systems, crypto-economic systems, but also more broadly governance systems and more higher level economic systems outside of the crypto space as well. And there are some examples of how protocols have achieved this. For example, dynamic minting is one of them. We also see that there are some protocols that are applying ways to dynamically mint and burn based on network utility. We'll take a look at one of those. And then one of the previous work that I also worked on is risk-adjusted bonding curves, which are hyperorganic, but they're hyperorganic in a very simple way. Essentially, they're hyperorganic because the parameter of risk changes with the current state. Let's take a look at actually risk-adjusted bonding curves. A static bonding curve has fixed a priori assumptions. Usually, it's things around a static risk, and so it cannot actually incorporate risk. And because of that, tokens get misallocated, and risk accumulates non-linearly over time. And so, in some kinds of scenarios, this kind of system can lead investors to get poor ROI and sometimes also lead to systemic collapse, which is a little bit more rare. So in a risk-adjusted bonding curve, mind you, now risk-adjusted bonding curves are better applied when it comes to projects projects rather than more market-efficient assets such as currencies. So these are the ways that it's applied. Essentially, the alpha parameter, which is the risk parameter, gets estimated continually by a prediction market. The prediction market enables for all agents to act as estimators of the risk parameter, and then when you collect it all and put it together, you're able to have a prediction market for the risk parameter. Now, hyperorganic policy, so now this is actually like going one level up, where we are not just adjusting the parameter, we're adjusting the monetary policy as well. Now, this is actually what we have applied in HUDL 01, which is the deepened protocol that I'm working on. And here, the slides are messed up, but here we essentially mint in proportion to all of the rewards that are earned by the contributors to the system. So anytime value is supplied to the system, then we mint tokens. And similarly, when value is contributed away from the system, so when our customers are actually using the bandwidth that's supplied across the network, then we burn. So essentially, we're able to have this dynamic supply model, which very accurately captures the amount of value that is stored in the network at that time. So if we don't get demand for a long time, you'll also see that reflected in the system, while at the same time, the system is so adaptive that if there is tremendous amounts of demand, then that doesn't push the token price up. Instead, it preserves the function of the token and ensures that all of the suppliers, such as media nodes and validators and orchestrators, are rewarded accordingly. So why do we need this today? I'm super excited for hyperorganic systems with today's technology because we have tremendous amounts of improvements in sensing. So this is the way that we acquire data. And we're able to acquire quite high integrity data because we have lots of advancements in the field of computer vision, space-based Earth observation and remote sensing, as well as hyperspectral imaging and quantum sensing. So we have access to high integrity data that is objective, right? We also have access to subjective data, which is generated by humans, but a lot of play area for us to also be generating and working with objective data that is coming from things such as Earth observation, and so on. Then processing has also had tremendous amounts of improvements. Of course, one of them being quantum computing. We're able to have much better compute today, much faster as well. Edge computing makes things a lot more efficient because we're doing everything at the user end, and also we can also have decentralized and open markets for compute. And finally, decision making, and perhaps this is probably what we are most excited about, is with the advent of artificial intelligence. Now, artificial intelligence has been around for a long time, but recently there has been advancements in explainable AI. And so all of the decisions that are made are crucially not a black box. Instead, they're able to show the reasoning process behind why certain decisions were made by the AI. And of course, reinforcement learning as well, especially as it is applied to multiple agents interacting with each other. Those can also be very useful, particularly RLHF. And why Web3? I mean, Web3 lays the foundation for all of this, because with Web3, we're able to have verifiability. Trust becomes inherent, so we don't actually need to have trust across multiple different participants in order to participate in such protocols, because they have full incentive alignment with the protocol itself. Every agent that is participating in the protocol is incentive aligned with the protocol, so participation becomes a no-brainer. And we are able to do this, of course, cryptographically as well as economically. So we have much stronger defenses against malicious action due to strong incentive alignment. Awesome. That's it for my talk, folks. Over here, we've got the light paper of Huddle, as well as the sign-ups if you want to read the full white paper. And here's my contact.
Thank you so much, Shruti. Very inspiring.